Hello, and welcome to The Space Above Us, episode 134, Space Shuttle Flight 60, STS-60, a new partnership. Last time, we talked about the first servicing mission to the Hubble Space Telescope, STS-61. Over the course of the most intense work week in history, we packed in 5 EVAs with dozens of hours logged outside of the spacecraft. Correcting Hubble's flawed mirror, replacing jittery solar arrays, and making various other upgrades to the orbiting observatory was a pivotal moment in the history of the Space Shuttle. The decades-long vision of a reusable spacecraft carrying a crew to a satellite and performing regular, planned, and a little unplanned maintenance had finally become a reality. So, not only did we rescue one of science's greatest assets, we also showed that NASA could take the next step in EVA complexity, and even bigger projects were possible. In the previous 2 episodes, we focused on the negative outcomes that can result from features on the micrometer and even nanometer scale. But not everything at that scale is problematic. At this point in history, the early 1990s, another technology found the word nanometer becoming more and more common: the manufacturing of integrated circuits. I don't think I'm breaking any news here when I say that the world runs on integrated circuits. There are dozens of them in your phone, in your watch, in your car, and most notably in your computer. For this next section, I think I'm in the clear, but in my usual overly cautious way, I'd like to point out that since this is a spaceflight podcast and not an electronics podcast, I'm just writing this off the top of my head and didn't do any proper research. So take it with a grain of salt. Or silicon. Anyway, integrated circuits are just what they sound like. It didn't take long after the invention of electronics for people to notice that certain circuits came up again and again. Rather than build it from scratch every time, what if they integrated these circuits ahead of time and put them in one easy-to-use form factor? So, if you needed a timer, instead of a bunch of transistors and wires and stuff, you would just have one little black chip with a few metal pins on it. Once these chips started housing increasingly powerful general-purpose CPUs, the next step was to try to fit more stuff into these integrated circuits, so you could make the overall device smaller or more capable. Eventually, the circuits became so small and so many were needed that using normal wires didn't really make sense anymore, so people started using lithography, using light to form tiny conductive circuits. For this process, you can just imagine somebody using a stencil and spray paint, but sort of in reverse. You start with a layer of conductive material, put a stencil in front of it, and use some special light and some special chemicals to melt away the exposed parts. If you made your stencil look like a bunch of wires arranged to make a circuit, congratulations, now you have a circuit. Traditionally, this has been done with silicon, since it's super abundant and easy to get at the required purity level to make itty-bitty circuitry. But as silicon circuits got smaller and smaller, more problems arose due to various reasons that are too in the weeds to get into. A possible solution was to use a material with some favorable characteristics called gallium arsenide. It might sound familiar, since we've already had a number of payloads dedicated to this material already. The reason gallium arsenide wasn't already being used in circuits, and the reason that it was flying on the shuttle, were one and the same. It had too many impurities. These impurities made it impossible to make super small circuits, but theoretically, if gallium arsenide could be properly purified, researchers believed that it would perform much better than silicon. So these experiments were trying to take advantage of the weightless environment to grow really pure crystals of gallium arsenide. If I understand correctly, this was actually working reasonably well, but what you really need in order to make integrated circuits is a thin film of this stuff, not a big old crystal. So, how do we make that happen? Epitaxy. No D&D players, not tabaxi, epitaxy. With epitaxy, a material is built up layer by layer at the atomic scale. I'm no expert in this, but to reuse an earlier example, I sort of imagine it like spray paint. By using some clever physics, it was possible to control a stream of individual molecules and just place them on a surface, building up a crystal layer by layer. If you could do this, then you could control the structure and get exactly what you wanted. I'm pretty sure there's more to it than just this, especially involving the crystalline structure, but that's the gist of it. But, can you see the problem with building up a material layer by layer at the atomic scale? How do you guarantee that only the atoms and molecules you want get added to the layer? Well, you get rid of them. If there are no other molecules, then there's nothing to interfere. Okay, great. So we just head down to the local vacuum chamber and get to work, right? Not quite. It turns out that even though we call it a vacuum, there can still be a fair amount of molecules bouncing around, just looking for a nice surface to bond onto. What we need is a vacuum with virtually no molecules at all. I think you can see where this is going. Let's build these thin films in space. Space is a vacuum, and it turns out that we fly there pretty often these days. But as we've learned time and time again, low Earth orbit actually has a fair amount of atmosphere still bouncing around. So while it's a pretty good vacuum, it's still not good enough. What we need is an ultra vacuum. And this is where we introduce the primary payload for today's mission, the Wake Shield Facility, or WSF. The 3.5 meter wide disc of stainless steel that we call the Wake Shield Facility is basically an umbrella for low Earth orbit. But instead of protecting a person from rain, we're going to protect our epitaxy experiment from atomic oxygen. I'm going to go ahead and say don't actually try this at home, but imagine driving down the highway in the rain while somebody holds an umbrella out the window pointed in the direction of travel. The umbrella is going to push the rain in front of it out of the way, and if you're going fast enough, the rain falling down from above won't have a chance to get to the bottom. So you would end up with this cone of dryness protected from the rain. And that's exactly what we're going to do with the Wake Shield Facility. By turning the flat disk that is the WSF into the direction of travel, the few pesky atoms that would normally be encountered in low Earth orbit get pushed out of the way, leaving a cone behind the disk that's almost completely empty. A cone of ultra-vacuum. On this side, the thin film gallium arsenide experiments could proceed completely undisturbed. Now, you may have noticed another problem here. This thing can block the tenuous atmosphere in low Earth orbit, but what about contamination from the shuttle? As we've learned, the shuttle is a big, noisy vehicle. It's outgassing, it's dumping water overboard, it's firing thrusters, it's emitting small clouds of all sorts of stuff. Fear not, because the Wake Shield Facility was one of these nifty little free-flying payloads. It had its own attitude control system, onboard electronics, and radio link back to the shuttle. We're going to release it and then drop back about 75 kilometers so it can work without worrying about orbiter contamination, which is pretty cool. So, who will get to carry this big flat metal space umbrella to orbit? Let's find out. Commanding this flight was our old buddy Charlie Bolden. Charlie Bolden has been with us since STS-61C, though we most recently saw him flying as commander on STS-45, the Atlas I mission. And while Bolden's role didn't really focus on the science payloads in the back of the orbiter, I would be remiss if I didn't use every mention of STS-45 to remind you that they fired crazy electron beams at the Earth, making artificial aurora. This flight marks Bolden's fourth and final mission, but don't worry, we'll see him again in another capacity a little bit down the road. If you can't wait though, depending on when you listen to this, you can always enjoy his introduction to the Space Shuttle Mission Simulator ride at the Kennedy Space Center Visitor Complex. Joining Bolden up front was another spaceflight vet, Ken Reitler. We last saw Reitler on his first flight, also piloting Space Shuttle Discovery, but that time it was on STS-48, which deployed the UR's environmental satellite. Like Bolden, this is also Reitler's final flight, but as far as I know, you can't see him introducing any theme park rides. Behind Reitler, we find Mission Specialist 1, Jan Davis. We know Davis from her flight on STS-47, which is also known as Space Lab J. I guess for this flight, Davis will be trading in Japanese for Russian. I wonder which one she would say is harder. In any case, this is our second of 3 flights. Next to Davis was Mission Specialist 2, Ron Sega. Ronald Sega was born on December 4th, 1952 in Cleveland, Ohio. He earned a bachelor's in math and physics from the U.S. Air Force Academy, followed shortly by a master's in physics from Ohio State. Later, he also picked up a doctorate in electrical engineering from the University of Colorado. With the Air Force, he learned how to fly, becoming an instructor pilot. He then returned to the Air Force Academy's physics department to construct a lab designed to investigate microwave fields. He'll continue to put his physics and engineering background to use as an astronaut, since he was one of the 2 principal investigators for the Wake Shield Facility. NASA selected him as an astronaut in 1990, and this is his first of 2 flights. Moving downstairs, Mission Specialist 3 is somebody who we're very familiar with at this point, Franklin Chang Diaz. This is the fourth time we've flown with Chang Diaz, with his most recent flight being on STS-46, which deployed Eureka and sort of deployed the tethered satellite system. Chang Diaz clearly has not had enough of space, though, since we'll be seeing him on 3 more missions in the years to come. And lastly, Mission Specialist 4, who is someone who's going to require a little explanation. For the first time on this show, we are introducing a crew member who has already spent time in orbit before joining our stage. But how can that be? I always include a brief biography for everybody's first flight. Is it possible that I missed a flight? Sort of, but it's more that these flights didn't really meet the criteria for the show. So now, flying for the third time, let's meet the veteran of Soyuz TM-7, Soyuz TM-12, and 2 lengthy stays on the space station Mir, Sergey Krikalev. A Russian. I'll explain later. Sergey Krikalev was born on August 27, 1958 in Leningrad, Russia, which is now St. Petersburg. He earned a degree in mechanical engineering from what was then called the Leningrad Mechanical Institute before joining NPO Energia, which was sort of the Soviet space program, but it turns out that's kind of a complicated topic. When he wasn't testing space equipment or developing ops for orbiting crews, he was flying as part of the National Aerobatic Flying Teams, winning multiple awards. In 1985, he was selected as a cosmonaut and began training to fly on Buran, the Soviet response to our space shuttle. In 1988 and 1991, Krikalev flew to Mir, completing 2 long-duration flights and racking up over a year in space. In fact, he was up there for so long that he launched as a citizen of the Soviet Union and landed as a citizen of Russia. His flight outlived the country that sent him there. Fun fact, remember how on STS-45, Charlie Bolden and the rest of the crew briefly spoke with the crew of Mir? It turns out that Krikalev was one of the Mir crew members he spoke to. Sergey Krikalev may have trained to fly on a different white and black spaceplane, but instead he will now become the first Russian to launch on an American spacecraft. We'll talk more about how in just a little bit. The launch was postponed a few times during long-term planning, but when launch day finally arrived, Space Shuttle Discovery encountered no delays or scrubs, lifting off on February 3, 1994 at 7:10 a.m. and soaring into a 350-kilometer high orbit with a 57-degree inclination. And actually, on that topic, I'm not sure why this mission had such a high inclination, so if anybody knows, please shoot me a message, jp@thespaceabove.us. Okay, before we really get started with this mission, I suppose I should explain what this Russian guy is doing here. First of all, and I'm just going to be blunt with you on this, I'm not going to be getting super in-depth into how the American and Russian space partnership came to be. My focus is on the missions themselves, not the politics behind them, so that kind of research is a little bit out of my wheelhouse. So, while I think I'll be able to give you enough context for the upcoming flights, if you're really interested in learning more, I'd encourage you to read about it yourself. Specifically, Ben Evans' book, Partnership in Space, has a great section about this flight and some of the wheelings and dealings that led to it. Today, I'm mostly just pulling from that. Also, just one more quick detour, many of you have asked about a recommended book list. I know I've been promising this for like 2 years now, but I really am working on a proper sources page for the site, which will include a book list. So just keep checking the spaceabove.us every now and then, and if it's not there yet, poke me with a sharp stick. Or send me an encouraging email, either way. Anyway, this clearly is not the first time that the US and Russia have cooperated in space. That's where the Apollo-Soyuz test project came from. So what happened after that? Why wasn't it followed up with another joint mission? Well, for one thing, on the American side, we were out of flyable rockets. In the wind down of the Apollo program, NASA only had the funding for Skylab, its 3 crews, and the Apollo-Soyuz test project. So that was a problem right off the bat. But also, outside the world of spaceflight, the 70s and 80s were not a great time for US-Russia relations. Leadership shifted, priorities changed, messages had to be sent, all that sort of stuff. The upshot is that nobody in a position to make it happen was particularly interested in working with the Russians in space. But as George H.W. Bush came into office, that started to change. Talks started back up about some sort of cooperative mission. This eventually led to a plan to fly several NASA astronauts on the Russian space station Mir and to fly some cosmonauts on the space shuttle. That would have been pretty cool on its own, but as the Soviet Union collapsed, the situation changed once more. I plan on covering this in more detail in a few flights, but the short version is that the US and Russia agreed to work together on building a new space station, which would eventually become the International Space Station. But first, it would be good to learn how to work together. NASA could benefit from Russia's experience with extremely long-duration missions, and Russia could benefit from the shuttle's capabilities and from an infusion of cash. So, with this flight, we're kicking off what we'll be calling the Shuttle Mir program. Officially, I'm pretty sure it's called ISS Phase 1, with the construction of the ISS itself being Phase 2, but I like Shuttle Mir better. For this flight, both Vladimir Titov and Sergey Krikalev moved to Houston in order to train as full-on mission specialists, with Krikalev getting the first flight. I think the distinction between calling them payload specialists and mission specialists is a small but important one. Both of these guys were spaceflight veterans, with orders of magnitude more time in orbit than the entire shuttle crew. But more important than that, for this partnership to work, everyone had to be treated like partners. I hope that this show has made clear that payload specialists are pretty incredible people who bring a lot to the spaceflight landscape, but they're not spaceflight professionals. So, I'm not sure if there was ever even a debate, but I'm glad to see that the cosmonauts were full mission specialists, just as trusted as anybody else on the team. Throughout this flight, Sergey Krikalev will be running experiments, doing maintenance, operating the robot arm, all the usual stuff. It's also worth noting that this partnership did not only exist in space. When the crew saw the adequate but small apartments that Titov and Krikalev had been given, they talked NASA into buying them and their families proper houses, and then took the Russians house hunting. They invited them to family outings, cookouts, church events, the works. They also tried their best to make the Russians feel comfortable in their new home away from home, even giving them driving lessons out of concern that the drivers around Houston might be a little more aggressive than they were used to. According to an anecdote in Evans's book, a NASA engineer later chuckled at the idea, because when Americans were finally exposed to Moscow traffic, the idea that the drivers in Houston might be a little too intense became laughable. Okay, that's enough about Shuttle Mir for this flight. More later, I promise. On flight day 3, it was time to begin the main highlight of the mission and deploy the Wake Shield facility. Mission specialist Jan Davis grappled the large disk and pointed the side with the Epitaxy experiment into the direction of travel. This might be surprising given the whole point of this experiment, but really they were using the atomic oxygen encountered in orbit to scour the face of the shield to make it completely clean. After a few hours of that, it was time to send the free-flying payload on its way, and that's when we hit our first snag. I'm not entirely sure why this was the method they went with, but the WSF had status lights built into it, which would change their configuration to let the astronauts know how the spacecraft was doing. I think it's similar to how the Agena targets for Gemini had little lights on the front, so the crews could tell if they were properly docked and what mode the Agena was in. Alright, fine, but these status lights were too dim to be seen in direct sunlight, leading to some confusion as to the state of the experiment. When they tried to troubleshoot this, they lost the radio link to the WSF, so this was not going great. Around 8 hours after it was unberthed, the Wake Shield facility was rebirthed in the payload bay while the crew slept. Meanwhile, engineers on the ground tried to figure out what had gone wrong. Indications were that the experiment was being hampered by multi-path radio interference. Essentially, the communication system was getting itself all mixed up thanks to interference caused by the signal bouncing around. But that's strange. They should have caught that when they did the electromagnetic interference test on the ground. This important test is when a spacecraft is loaded into a special chamber and its communication system is put through its paces to ensure that this exact situation doesn't happen once it gets to space. So, why was the crew seeing this problem now? Hadn't the Wake Shield facility passed its EMI test? Well, it turns out there was no EMI test. This flight was in the early part of the tenure of NASA Administrator Dan Golden, who was a big proponent of the cheaper, faster, better approach to space missions. I haven't actually had a chance to read in depth about this yet, but my understanding is that this approach essentially encouraged missions to accept more risk in order to bring down costs and schedules. To me, it sounds similar to the Starship development program that SpaceX has been doing in southern Texas. They just quickly crank out prototypes and test them as is and see how it goes. By using this method, the Wake Shield facility went from concept to orbit in only 5 years and for only $12 million. And in the context of spaceflight, that is ridiculously cheap. But cheaper, faster, better is a double-edged sword. Yeah, you're going to fly more missions and you'll fly them cheaper. But you have to be willing to accept that extra risk. Though, let's be careful not to conflate risk and safety here. I don't think safety was ever consciously on the table. The risk here was that the mission might fail, and you came all the way up here for nothing. And that certainly looks to be what's happening with the WSF. If you're going to move fast and break things, you have to be okay with things actually occasionally breaking. And that can be a hard sell when people are investing years of their lives into a project and dedicating one of a few precious payload slots on the shuttle. The next day, the crew woke up and gave the wake shield facility another shot, but after hours more debugging, the situation did not look good. It was possible that they could still release it, but it was also possible that it would then become uncontrollable. And that could be dangerous to the crew and orbiter, and would require rapid development of contingency recovery plans, which there wasn't really time to do. So, instead of flying on its own, the WSF would stay securely fastened to the end of the robot arm while the epitaxy experiments were performed. To be fair, that was still pretty good, but it wouldn't achieve the same level of vacuum as the original plan, so that was definitely a letdown. Plus, the pilot crew missed out on a cool rendezvous mission. Fear not, though, the results were promising enough that the wake shield facility will fly again in just a little bit. Stay tuned. Turning our attention inside, it turns out that there's a whole other major system in the payload bay that I haven't even mentioned yet. SpaceHab. That's right, the commercial competitor to Space Lab was back for its second flight. Inside was another slew of miscellaneous experiments that I am just going to flagrantly skip for time. Though I will mention that Astroculture, the experiment hoping to grow plants in space, was back for its third incremental test. This time they were checking that the humidity levels could be properly controlled. I bring this up because I have no idea if this thing will ever actually grow plants in space, but I've enjoyed watching its slow, plodding road to giving it a shot. Something I will mention about SpaceHab on this flight was the air duct from the orbiter to the pressurized module. There's nothing really fancy about this. There's just a pipe coming from the orbiter and bringing fresh air into SpaceHab, so the crew doesn't encounter any nasty, stale air bubbles. Early on in the flight, it was observed that a rubber section of this duct had sort of collapsed down on itself. As Charlie Bolden tells it in an oral history, the crew duly informed Mission Control, who acknowledged the problem, and everybody went back to their usual routines. Sergey Krikalev, however, was sort of baffled. He suggested that they, just fix it. And the crew said, no, they'll wait for Mission Control to get back to them. Okay, fine. Several days later, Franklin Chang Diaz was doing a live video tour of the shuttle for some school children in his home country of Costa Rica. At one point, he either casually pointed out the crimped duct, or it was just seen in the background, I'm not really sure. But in any case, mission controllers saw that the duct was almost completely closed, and they were surprised, saying they didn't realize it was that bad. They told the crew they'd give them a solution soon. For Krikalev, this remained baffling. He had spent over a year living on Mir, which didn't have the benefit of a geostationary or even global communications network. The cosmonauts mostly only had communications with the ground when they were over Russia. This meant that they could go hours with no contact at all. So they were used to fixing problems on their own and, then maybe telling the ground about it later. So Krikalev again said, let's just fix this. If this happened on Mir, I wouldn't have even told them about this. Alright, fine. The crew pulled the section of duct out, tore a rigid cover off of a map book that they had on board, curled the cover into a cylinder about the size of the duct, and slid it inside. The rigid cover did the trick, propping open the duct and solving the problem. When Mission Control was later informed of the solution, they didn't have any comment, but once everybody was back home, Bolden was approached and told that they wished he hadn't just gone and done it. The ground controller said that if the crew just said their plan, it would have been approved, but they didn't like that they just went and did it. Though, I kind of have to sympathize with the crew who had been waiting for an answer for days. It was an inconsequential little slice of the mission, but I think it's an interesting bit of foreshadowing, showing that NASA and Russia had pretty different approaches to spaceflight, which would lead to more than a few surprises in the future. And speaking of Mir, one of my favorite payloads, the Shuttle Amateur Radio Experiment, was once again flying today. The ham radio setup was used to contact the crew of Mir, and once again Charlie Bolden found himself chatting with the crew of a Russian space station. But this time Sergey Krikalev was a little bit closer. As usual, the crew also chatted with a number of schools where kids got to ask questions about space. One notable school on the list was the House of Science and Technology for Youth in central Moscow. The American crew couldn't really converse with the Russian kids, but they could say a few rehearsed lines. In fact, despite it not really being necessary for this mission, the crew thought it would be a nice gesture to their cosmonaut guest if they learned some Russian and began taking lessons. Among the lessons was a common Russian lullaby, which the crew sang over the radio for the school children in Moscow. I'm sure their accents were impeccable. On flight day 9, it was time to close the hatch on Spacehab, pack everything up, put the launch and entry suits back on, and prepare to come home. In what is practically a tradition at this point, the weather in Florida resulted in one extra trip around the world, but I'm sure that nobody was complaining. Least of all Charlie Bolden, who had decided before the flight that this would be his final mission. In an oral history interview, he talked about the view during that final entry. Looking out the orbiter windshield, he could see northern Canada on the left and all the way down to Florida on the right, including the gap in the storms that Discovery would soon be threading through. Being an astronaut isn't always easy. The job demands a lot of sacrifices, the hours are long, the work is dangerous, and the pay is nothing amazing. But it sure does have some pretty incredible perks. After 8 days, 7 hours, 9 minutes, and 22 seconds, Discovery eased down onto the runway at the Shuttle landing facility. Between the gentle re-entry and the graceful landing, I'm sure it was quite a change of pace for Sergey Krikalev. On his previous 2 trips home, he landed in the Soyuz descent module, and I've seen its touchdowns likened to a mild car accident. But then again, any landing you can walk away from. As is often the case when hosting international crew members, the crew of STS-60 was invited to visit their foreign crewmates' homeland. So it was that Charlie Bolden and Ken Reitler, both of them aviators and test pilots for the Marines and Navy respectively, found themselves standing on the walls of the Kremlin, admiring the view of Red Square. After a lifetime of training to destroy this place, they had been welcomed as friends. Clearly a shift had been made, and there were some exciting things to come. Though not everything had changed. If there was ever any doubt, it was dispelled when Bolden, in his hotel room with his wife, said how he really wished he had a Coca-Cola. 5 minutes later, someone from the hotel staff knocked on the door to ask if he could get them anything. Perhaps some water, maybe a Coke. Oh, Russia. Real quick, before we get to the outro, I just wanted to say that I now have a P.O. box. I have no earthly idea why you would want to send me something, but since I've seen other podcasts offer it, I figured I would as well. The address is under the contact section at thespaceabove.us. Also, since I already broke the flow of the outro, I'll mention again that the show has a Patreon available at patreon.com/thespaceaboveus. There's nothing essential on it, since I didn't want to deprive listeners of anything that belonged in the main show, but there are some fun extras. One recent addition was a podcast mini-episode where I only had 2 hours to make as good an episode as possible, starting at the moment when I learned the patron-submitted topic. So if you'd like to hear me rush through a half-baked episode about lunar landing hoaxes, now is your chance. Next time, Columbia flies again, and I try not to mix up the U.S. microgravity payload with the U.S. microgravity laboratory. Ad Astra, catch you on the next pass.